Hey guys, today I want to present a solution to the Italy Math Olympiad 2019 problem 2. At first, let's have a look on the problem statement. We are given two primes, p and q, and we are given that p plus q squared is a perfect square. Now we have to prove that p squared plus q to the power of n is not a perfect square for every positive integer n. At first, we want to use the condition that p plus q squared is a perfect square, and therefore we can write down that p plus q squared is equal to k squared, where k is a positive integer. As always, in number theory problems, it's a good idea to try to factor some things, and therefore we want to bring the q squared onto the right hand side. So this is equivalent to p is equal to k squared minus q squared, and now we can factor this. This is namely k minus q times k plus q. Now we remember that we have given that p is a prime number, and now on the right hand side we have a product of two numbers, and since this number here is clearly positive and greater than 1 because q is a prime number, we know that the second factor here must be equal to 1. So let's write down that k minus q is equal to 1, and this gives us directly that k is equal to q plus 1. So now if you plug in k into this factor here, we get that p is equal to 1 times 2q plus 1, which is 2 times q plus 1. Now we find a correlation between p and q, and this is really nice, and therefore we can now have a look on this second term here in the problem statement. We want to prove that this is never a perfect square, and therefore we want to try to do a proof by contradiction, and so assume that p squared plus q to the power of n is a square, namely m squared. Here we can try a similar factorization than in our first equation here, and we can bring the p squared to the right hand side. So we get that q to the power of n is equal to m squared minus p squared, and now this is equal to m minus p times m plus p. Now, since also q is a prime number, we know that on the right hand side both factors must be powers of q. But now, if both powers here are greater than 1, we know that q must divide both of these factors here. But this seems really unlikely, so let's have a closer look what exactly happens in this case. So we have the first case that m minus p is greater than 1, and clearly m plus p is also greater than 1, and so we get that q must divide m minus p and q must divide m plus p. But this gives now that q also divides the difference of the two right hand sides. So q divides m plus p minus m minus p, which is nothing but 2p. And now we can use this equation here. So we get that this is equal to 4 times q plus 2. And this directly gives us that q divides 2, which means that q is equal to 2. Now when we use this equation here again, we directly get that p is equal to 5. Now plugging in the values for q and p into this equation here, we get that 2 to the power of n is equal to m minus 5 times m plus 5. Now we have two factors here on the right hand side, and both of them must be a power of 2, but the difference is 10, so we have two powers of 2 with difference 10, and this is not possible. So this is a contradiction. So now we got a contradiction in the first case that m minus p is greater than 1. Therefore we are now in our second case that m minus p is equal to 1, and from this we directly get that m is equal to p plus 1. This equation here gives now that q to the power of n is equal to 1 times n plus p, which is nothing but 2p plus 1. And now we can use this equation here again and get that this is equal to 4 times q plus 3. But this now directly gives us that q divides the right hand side, which is 4q plus 3, and therefore q divides 3. But now, since q is a prime number, we know that q is equal to 3. But now we can plug q equals 3 into this equation here and get that 3 to the power of n is equal to 4 times 3 plus 3, which is equal to 15. But 15 is for sure not a power of 3, and therefore this is also a contradiction. All in all, we have in every case when p squared plus q to the power of n is equal to m squared a contradiction. Therefore, this is not possible, and we are done.